everyone, so in this video we are talking about geometric sequences. So we've already done arithmetic sequences, this is on geometric. To get us started, go ahead and take a second and look at just these patterns here. Math is really just the study of patterns. And so, how do you think C is different from these first two? So you may have noticed this pattern is just adding 2 each time. This pattern is subtracting 4 each time. But this pattern is doubling each time. It's times 2, and then times 2 again, and times 2 again. This right here is a geometric sequence. So it's geometric because the pattern is multiplying the same number over and over again, rather than adding or subtracting. These are arithmetic sequences that we already talked about in the linear unit. Keep in mind, as we're working on this stuff, sequences are just functions. The input is like, what term number are you going to be at? So for example, in this sequence, this is term number 1, term number 2, term number 3, term number 4, and so on. We often call this A1 equals 2, A2 equals 4, A3 equals 8. We just use A to say that it's a sequence, and then the little subscript here represents the term number itself. And then the actual term is like the output. So if I want to know A50, I'm asking what is the 50th term in the sequence, and then I see what that is. It's basically the equivalent of having a function and then plugging in a value like 50. These are pretty much the same thing. So keep in mind, sequences are just functions, where you put in the term number and you get out the term. An arithmetic sequence is basically just a linear function because you're adding or subtracting the same number each time, but a geometric sequence is an exponential function because you're multiplying by the same number each time. Again, with arithmetic sequences, that number you add each time is called the common difference, D. With geometric sequences, we call it the common ratio, R. And R just stands for ratio. It's the number that you multiply by to get to the next term. So like in this one here, our common ratio was 2. I would say R is 2, because that's what I multiply by each time. We call it a ratio because if you were to take a term and divide it by the term before it, like a ratio, you would get the R value. So 8 divided by 4, 16 divided by 8, and so on. All right, so go ahead and try these. Find the common ratio for each of these sequences. So hopefully you've had a chance to try it. This one we already talked about. The R value here is 2 because it's multiplying by 2 each time. And this one doesn't actually have a common ratio. At first it's times 5, but then 5 times 5 is 25, not 10. Then we jump to like adding 5 each time. So this one is actually not geometric, and it's not arithmetic either, because we're not multiplying by the same number each time, and we're not adding by the same number each time. Let's try this one. So this one's a little weird because it's going down, it's decreasing. This is actually exponential decay rather than exponential growth. Again, if you're not sure what the ratio is, you can always take a term and divide by the term before it and see what you get, like 2 divided by 4, or 1 divided by 2, or even 0.5 divided by 1. Each of those answers gives you 0.5 or a half. So basically we're multiplying by a half each time, or 0.5. Or you might think of that as like dividing by 2 each time, which is the same as multiplying by a half. Division is just multiplication. So in this case, the R value is 0.5 or 1/2. And then this one, you may notice how it goes from positive to negative, it kind of jumps back and forth. So in this case, our R value is going to have to be negative. to get from 4 to negative 12, we'd have to multiply by negative 3 and then make sure that works. Times negative 3 times negative 3, yeah, it works. So my R value is negative 3. It's called a geometric sequence because it matches up with geometry. For example, if I had an R and then times another R, it'd be an R squared, and then times another R would be an R cubed. You can basically imagine like just one R would be like the length of a segment R, and then if I had a square that was like R times R, I get R squared, and then if you did R times R times R, that would be like the volume of a cube. Basically, it just matches up to these geometrically, so we call it a geometric sequence. And then if you go into 4 dimensions, we can't really visualize that. Okay, so take some time and try these. See if you can figure out if it's geometric, and if it is, find the common ratio. So pause the video and try that, and then you can watch me go over it. This one is multiplying by negative 6 each time. So since it's multiplying by negative 6, yes, it is geometric. The R value is negative 6. This one, to get from negative 1 to 1, you'd have to multiply by a negative 1. And to get from 1 to 4, you'd have to multiply by 4. Since those are different numbers, this is not geometric. This is a cool pattern. You add 2, you add 3, you add 4, but it's not geometric sequence. This one looks like it's times 5. Let's make sure that holds up. 15 times 5, and this times 5. Yeah, so that one is geometric. The R value is 5. This one is doing plus 2 each time. That's an arithmetic sequence, not geometric. And then this one, it might be kind of hard to figure out what is the R value here. So again, remember that trick of you can take a number and divide it by the one before it. So if I do 3.56 divided by 2, let's see what we get. So 3.56 divided by 2, and it's 1.78. So that's what I would multiply by each time. Let's see if that works. So times 1.78 here. If I do 3.56 times 1.78, will I get this? And yes, I will. So that worked. And then try it one more time, and that will work as well. So in this case, the R value is 1.78, and it is geometric. Okay, so now that we know how these work, again, just a reminder, if you're adding or subtracting a number each time, it's a linear function. Those arithmetic sequences are linear functions. And then if you multiply or divide by the same number over and over, it's a geometric sequence, which is really just an exponential function, because it's going to get bigger and bigger more and more rapidly, like an exponential function. Okay, the goal for this kind of stuff is, since it's basically a function, can we come up with that equation? Instead of doing f of x, again, we'll use a n, but if you want to use f of x, you can. Either way, I want to come up with some sort of equation to where I could plug in an n value to be like, I want to know the 50th term, what is it? And the function would spit out the term for you. There are 2 ways to do this. It's going to be similar to what we did with arithmetic sequences. The first is called a recursive formula. You're not as familiar with these. Recursive, if something recurs, it's kind of built on itself, it repeats. And so let me show you how it works, and then I'll show you what's on your formula sheet. You're probably pretty familiar with this sequence by now. It just doubles each time. This is kind of like the zombie scenario we talked about in class, where your zombies are doubling each encounter you have. A recursive formula looks like this. It says, if I want to know a term, I just take the term before it, and then what do? I multiply by 2, so times 2. That's pretty much it. There's a slightly mathier way to say the term before it. It's, if this is a n, then I want a n minus 1. Because like, say this were 50, then I would want the 49th term. Say this were 100, I would want the 99th term, and then still just times 2. So this is just a mathy way to say the term before this one. And there we go, that's a recursive formula. Take the term before it, multiply it by whatever your common ratio is. You also need a starting point. So like, I can't go back forever. I need to say like, at some point, you've got to start here. So typically with a recursive formula, we say, by the way, A1 is 2, because my first term was 2. And so this would be a recursive formula for this situation. So it looks like this. This is on your formula sheet if you need it. You always say what A1 is. It's just fill in the first term. And then to find any term AN, you take the term before it, multiplied by the common ratio. You're going to leave the in values. So if you want to come up with a formula, leave in. That's kind of like the x. You just leave it in the equation. All you need to do is fill in R and fill in the first term. And that's it. Let's try another one here. This one gives us the recursive formula. It says that the first term is 2. And then in this situation, to find any other term, we take the term before it and do times 3. I want to find the first 5 terms. I already know the first term is 2. How do I find the next term? Well, just do times 3. So 2 times 3 is 6. 6 times 3 is 18. 18 times 3, I'm not exactly sure. Let me just make sure. Is 54, and then 54 times 3 is 162. And there's the first 5 terms. Just to be clear about what's happening here, I was trying to, this is A2. Right here, this is the second term, A2. So I was doing this formula, which is A, and n is currently 2, so I'm going to do 2 minus 1 times 3. 2 minus 1 is just 1. So basically, I'm just taking A1 times 3. And A1 was 2. It was the first term. It was the term right before this. So I was taking 2 times 3, which is how I got the 6. The same works for any of these, right? Like if I wanted A5, which is this one, I'm doing A5 minus 1 times 3, which is really just A4 times 3, the term before it, times 3. Okay. The problem with, well, let's do one more. To write a recursive formula, you start with the first term, which in this case is 18, and then for any term after that, you just take the term before it and multiply by the common ratio. In this case, we're dividing by 3 each time. So I could do divided by 3, or if I want to multiply, I could say multiplied by 1/3. Because 1/3 of 18 is 6, 1/3 of 6 is 2. You could put the 1/3 in the front or in the back, doesn't matter. The problem with recursive formulas is, let's say I want to know a very big term, like the 100th term. If I want to know the 100th term, I would need to know the 99th term, the term before it, times 1/3. But I don't know the 99th term, so I would have to know the 98th, and to get the 98th, I would need the 97th, all the way back to the first term. And so this is kind of going to be an intense process. It would be better if I could just explicitly plug in 100 and get out the term without having to keep working backwards. So that is called an explicit formula. In the explicit formula, you plug in the same things. You're going to have a first term, A1, and then the common ratio, and that's all you have to fill in. You leave the ends where they are, and you'll see how this works in just a second. So these are nicer because you can just plug in whatever you need. For example, if I want to find the first 5 terms with this sequence here, I just plug in 1, 2, 3, 4, and 5 for n. Or if I want to know the 10th term, I plug in 10 for n. It's basically working like an x. So like if I want to know the first term, A1, I'll just plug in 1, which is, you can put that on your calculator if you want, but that's -4 times 3 to the 0, which is 1, so -4. And you can actually see that in your equation too. This is A1 right here in the front. So my first term is -4. And then you can kind of see from the formula that we're just going to do times 3 each time. But if you weren't sure, you could do A2 and just plug in a 2. So -4 times 3 to the 2 minus 1 power, which is -4 times 3, which is -12. And yeah, we see that happening. So it was times 3, and then we'll do times 3 again, and then times 3 again. And then times 3 again. And then if I want to know the 10th term, plug in 10. So A10 equals -4 times 3 to the 10 minus 1, which is -4 times 3 to the 9th. I'm going to put all that in my calculator, which is -78,732. So I could have just kept multiplying by 3 over and over again, but it was easier just to plug in 10, see what you get out. All right, let's actually write our own now. I want to write an explicit formula for this sequence here. I need to know the first term, which is 18. And I also need to know the common ratio, which we've talked about this one already, is 1/3, because you're dividing by 3 each time. So basically just fill in the formula. It looks like this. Just fill in 18 for A1, and just fill in 1/3 for R. Again, you leave the n part because that's part of your equation. You want to be able to plug in anything for n. And so that's it. Remember that you can't multiply these because the exponent is attached to this, and exponents comes first. So you can't really do anything with that. You just leave it as it is. And that's your explicit formula. If I wanted to find the 50th term, I could plug in 50 for n and see what I get out. You may sometimes see this written instead of an. You may see it written as f of x. And again, it just means the same thing. So if you have this, it's literally the exact same thing as this right here. N or x, it means the same thing. Let's see. Oh, I wanted to talk about why we do we use n minus 1. We use n minus 1 because basically what this is doing is saying you start with 18 and then you just multiply by 1/3 and 1/3 again and 1/3 again. So it feels like it should be 18 just times 1/3 to the n power. However, you don't multiply the very first term by the 1/3. So the n minus 1 is basically dealing with that for us. So by the time I get to the second term, I only want to multiply by 1/3 one time. And by the time I get to the third term, I only want to multiply by 2 1/3s. Basically, it's always the term number minus 1, and that's where the n minus 1 is coming from. If you forget that, that's okay. Just use what's on your formula sheet. And I think that's it.